Welcome to the session of CFD, an introduction to CFD. In this session, we will clearly explain what is CFD and why we need CFD and how the CFD actually works. Okay, so let us start from the term that is CFD. Hope you all heard about this term, that is computational fluid dynamics. So it is a part of analysis. We have so many analysis in the workbench. We see explicit analysis. Like that, CFD is also a domain of certain analysis. Okay. By using CFD, we calculate or predicting the flow of fluid and in sometimes heat and mass transfer and chemical reactions and related phenomena. So CFD has a wide varieties of engineering process. So in all stages of the engineering process, we use a CFD, right from the conceptual study of a new design and detailed product development, that is new product development, and optimization of the particular design and troubleshooting any errors in that particular model and redesign of the model. Okay. So the CFD uses the CFD solver to calculate that any phenomena, right, flow of a fluid or whatever it is. So basically it uses some set of equations. Okay, so that is conservation of mass, so one kind of equation, and momentum and energy. So we usually turn on the energy equation. So when we are working on a heat related problem, like, so we have a heat and mass transfer terms, right? So when we use to calculate that particular term, we have to turn on this equation. Okay, so we will discuss in the upcoming slide. So that includes how the CFD solver is actually works. Okay. Apart from that, a CFD analysis complements the test of experiments, testing and experimentation by reducing the total effort. So they it actually works in the method of numerical, right? So CFD analysis is a numerical method. So in the early stage of Ansys workbench, we discussed about the term called validation. Validation. What is validation? So validation means we need to verify, okay, this model is okay or not, whether it is satisfies the customer need or not. Okay. So that is the ultimate responsibility of a CAE engineer. So the responsibility of a CAE engineer is to validate the particular design, whether it is okay or not, and give it as an NOC, that is no objection certificate. So throughout this we have a various validation methods. So that is analytical method and numerical method and experimentation method. So these analytical method takes much time, and when the problem is too complicated, the solving time is also increases. Okay. The experimental method is okay, but the time taking and then cost wise is very expensive. So that is why we don't usually we use experiment, but occasionally we use this experimental method. So at the last stage of the analysis, most of the time we only depend upon the numerical method. So in this numerical method, CFD is also comes under the numerical method. Okay. So that is why it's very economic to use the CFD analysis. Okay. So I will move on to the next slide. This slides explain how the CFD analysis actually works. Okay. So Ansys CFD solver basically works on the finite volume method. You all heard about the term in the numerical method session. We already explained in the workbench. So we have various numerical methods like finite element method and boundary volume method, finite volume method and finite reference method. So the one kind of method is finite volume. So the CFD uses this method. Okay. Basically in CFD analysis, we have so many terms like walls, domains. So domains is nothing but the region of analysis. So for example, if you have a fluid, so we call it as a domain. Okay, that fluid domain. So it is discretized into a finite sets of controlled volume. Okay, controlled volume or controlled volume. So the discretization, which is nothing but meshing, and you are all familiar with this term, what is meshing, and we say it as sometimes that is called discretization. We break into a infinite stage to finite stage through meshing. Okay, and we have the general conservation of equation for masses, momentum, and energy and species. So that is what I explained in that previous slide. Okay, so we have a set of equation. The CFD solver will uses that equation to get the actual results. Okay, so this is the conservation of equation. So this name that the first term is unsteady, and then conservation, convection, diffusion, generation, like that. Okay, so if you include any temperature related thing, so the convection equation is turned on, otherwise it won't. Okay, so if you include diffusion, this equation part will be turned on. Okay, but if you are using a laminar flow other than a turbulent flow, so this unsteady will not included, and if you don't use any temperature related thing, so this factor will not included. So if you don't use diffusion, this part gonna not used. So if you suppress these things, so as well as the problem complexity will be decreases, the size of the equation will also decreases. If you included the more terms, the equation size will be much more bigger. Okay, so basically this CFD analysis is uses a iterative solver. It's a convergence based solver. We'll have a dedicated topic on what is convergence in that upcoming slides. I'll explain in that particular slide. So what is convergence, how it actually works. Okay, so it's a partial differential equations are discretized into a system of algebraic equation. So we already see this example in that workbench session. So basically we have a set of equation, and then we calculated as a stiffness matrix, and then that matrix will be converted into a simultaneous equation, and we solve that equations. So that is what they say that. So partial equations is solved in the system of algebraic equation, then we get the actual results. Fine, I'll move on to the next slide. That is basically we have a various steps which should be in our mind while we do a CFD analysis. Okay, so totally we have a 7 steps. We will see one by one. Okay, so the step number 1 is a modeling goal. Okay, so what is that modeling goal? So we have to be very clear what are the results we are looking for, like whether you want to know about the pressure drop or mass flow, and how will they used. So why we are looking for that particular result. Accordingly, we need to design our model. Okay, so that is what they say, that modeling goals. And what are your modeling option? So how can I make my model as simple as possible? Okay, so if you are having a symmetric model, you can use the condition called symmetricity or periodicity. It's up to you. And what are the simplification you assume do you have to make? Like the assumptions we make, we have linear analysis, non-linear and workbench, right? So that is why what we can assume at the initial stage. So whether it may be a constant velocity or a constant pressure, or maybe it's symmetrical condition, you can assume. And what physical model will you need to be included in your analysis? So what is the domain I actually design? So you don't need to design the entire model of the component. Okay, so the CFD is used in all the stages. Right, from if you want to design a car, so obviously you need to do a aerodynamic analysis, right? So for that you don't need to design or model the entire thing so inside the car. So only the aerodynamic analysis will take place on the outer surfaces of the car. So you just created a outer surfaces of the car and do the analysis, right? So that is what they actually said, that physical models what you need to include it in your analysis. Okay, and what degree of accuracy you need, and how quickly you need the result. So these two terms is connected with each other. So when we need a high accuracy, the result will take a much more longer time, and if the degree of accuracy is decreases, the solving time will be drastically decreases. So it greatly depends upon the quality of the mesh. So the quality of the mesh is very important term in CFD. So if you don't have a well and good mesh, your problem will never converge. Okay, so we'll discuss about the convergence in that upcoming slides. So it should be more clear. So what should be the accuracy you require, and how quickly the results will be you needed. So most of the time, so we decide the accuracy rate depend upon the availability of the time. Okay. And then last question is CFD is an appropriate tool for this analysis? Okay. So you should be very clear. Okay. So whether should I go for CFD analysis, or else I can solve the same problem by using any other systems. Like we have various types of analysis. So you can do the thermal analysis on CFD analysis, or else you can solve the same problem in Workbench also. Okay. So if it is needed the CFD, then you can came here for, or else you have a analysis that explicit also you can do. Okay. So that will be, you should be more clear. Fine. So the step number 2 is identify the domains. Okay. So most of the peoples will make a mistake over here. So they model the entire thing and give the entire model to that CFD part and try to mesh that. They will end up with the meshing. Okay. So if you have a more number of meshing, obviously the problem will take 3 to 4 days to solve the particular problem. Okay, you will have a more number of nodes. Okay. Identify your domains means where my analysis actually take place. What's my calculation region? So in this problem, it's a best example. So we have a pipe on this end, and you have a pipe on this end, and here also. So the liquid is actually entered here, and it's outlet. We have one outlet over here and one outlet over here. Actually, my analysis only I'm interested in this region. So this part. So the part number 1. Okay. So what you're going to do here, you don't need to model the entire thing, right? The whole thing. Okay. So only you can model this region. Okay. So why it is? Because if you assume that the initial velocity of the liquid, so this is the region of the liquids, actually flow from this end to this end, right? So when I cut this model here, so the velocity of the liquid in this end will be exactly equal to this end. Okay, so for example, if it's a 5 meter per second, so it doesn't changes over here also. It's similarly it having the value of 5 meter second from here itself. So I can cut the model, I can delete this. So you don't need to include at that. So you can start from here itself, because the analysis is actually take place from here itself. Okay. So it's very important thing. So you need to how will you isolate the piece of complete physical system? So where the result is interested, the domain of interest as a part of large system. Okay. So only the model will be included in this. So we only cut this model and try to mesh it and give the boundary condition as we needed. So where will be the computational domain? This begins and end. That is very, very important. It's actually started here and ended here. So what is the inlet, outlet, what will be the wall condition, everything will be you have to define. So that is what they try to explain here. And also if the problem you don't need to always include a 3D model in a CFD analysis. Usually if your problem can be done by using 2D, you can go for 3D, or else if it is an axisymmetric problem, you can use axisymmetric also. So how simple you can model the domain. So that is very, very important thing. Good. So I will move on to the next slide, that is the creation of solid model domain. Okay, so what is the creation of solid model domain? I will explain as simple as possible. So we'll have two models. The one is original CAD part. So this is a pipe section, a T junction. So we have a pipe over here and here. So you may clearly notice that the pipe has some thickness over here. So one is the inner radius and then outer radius. The fluid will takes the inner radius, right? So the fluid is actually flow inside the pipes. Okay, there is nothing connection to the outer this connecting phases. We have a hole like this region. So we are only interested in the fluid region. So instead of creating the entire model, you can only create or extract the fluid region. So while this analysis is actually take place, so this is the region we actually do the analysis. So you should be more clear. For a simple model, it will be very easy to extract. For a complicated model, you need to think of okay, so where the analysis is actually take place. We don't design the entire CAD model for a CFD analysis. We only design the fluid region. So in which domain the fluid analysis is actually take places. So that is what you need to do here. I just modeled the fluid region in this CAD model. Okay, and also you should be very clear which should I remove. So the unnecessary features like the bolt, fillets, so we don't actually needed that, I just removed it. And make use out of the symmetry and periodicity conditions. So and sometimes you don't need to model the entire thing, you can use the symmetrical conditions also. And do you need to split this model so that the boundary conditions or domain cannot be created? So you should be more clear. So when you cut the model, it should never disturb the boundary conditions of that particular problem. So otherwise you don't need to, you can't split that particular model. So that is called the creation of solid models, like a domain creation. Okay, so it should be more clear when creating the domain, not the entire CAD model. So this is the step number 3. And step number 4 is design and creation of meshing. So as I said before, a meshing plays a major role. So if you don't create a well and good proper mesh, your problem will never converge, because in Workbench itself it may be solve the problem, you will get a result, but here itself it's a iterative solver. Obviously your problem should converge. So for that you need a well and good mesh. So what degree of resolution required for each region? Okay, so the resolution means the quality of the mesh. So in this domain, okay, so I will say an example. We have a pipe section like this. So I know that when a liquid flows from here, so it has a maximum turbulence nearby this region because the volume is contracted nearby the edge. So obviously you have a more number of turbulence nearby this edge of the liquid. Okay, so you need to create a proper mesh nearby this region unless or until you can't observe what has exactly happened in this region. Okay, so you need to create a proper mesh or a fine mesh nearby this region, and you can create a more or coarse mesh nearby this region. Okay, so that is what the degree of resolution is required for each region of the domain. Okay, so can you predict the region of high gradients? So that is what this region is, a high gradient region. So here is the resultant area. So we need to create a more precision of the meshing. And will you use a adaptation to add a resolution? So we have an adaptive size function. It's an automatic procedure for Ansys Workbench. So in CFD also you can use this option. And what type of mesh is more appropriate? That means either it may be a quad or it may be a tria. So we can either use this. So quad and tria is for 2D and hex is tetra for 3D, but we don't usually uses this triangular mesh. We only uses quad for, because you know that reason, the triangular element is more stiffer than this quad. So that is why we always prefer to quad and hex mesh, but it's very difficult to create for a complicated structure, but still it takes some time. You may use this mesh. And the next thing is, do you have a sufficient computer resource? Most of the peoples will make a mistake on this particular region, whether they have a sufficient computer resources or not. By using a simple laptop, you can't solve a complicated problems, especially a 3D problem. So most peoples will ask us, oh, sir, I want to model this 3D component in a CFD analysis. You can't. Okay. So when you try to say, for example, this is a interior of a car design. Okay, so when I try to mesh the whole body, obviously you have a lakhs and lakhs of nodes and elements. So it will take some days to solve the problem. So like this component, you only measures or solve the problem by using servers, not on a laptops. A server based solvers will use it to execute a big problem, having a lakhs and lakhs of nodes. Okay, so even though a service is also takes a 3 to 4 days to solve the problem, and again it shows an error, so the problem is not converged, and then you have to work again. So that is why I am saying that make sure do have a sufficient computer resource. So still, if you are using a student's version, you will be limited to a nodes and elements counts. That is for Workbench itself, you have a node counts of 32k nodes. Beyond that limit, the problem will not get solved. And for CFD analysis, you'll have a limitation of 52k nodes. So when you try to mesh more than the 52k nodes, the problem will not get initiated. Okay, so that is the drawback of student's version. So if you are using a cracked version, so that is not an issue. Okay, let's move on to the next step, that is step 5, setup and solve. That is creation of regions, whether it is what is inlet and what is outlet, that is. So you need to define the material properties like fluids, so maybe water or air, you need to define, and solid and mixture also. Once it is settled, the creation of material, and you need to select the physical models. We call it as a turbulence and then combustion and multi-phases problem. You need to define that. So what type of turbulences happen to, whether it is laminar or some other like K epsilon, or we have varieties of turbulent flow. So you need to define the turbulence of the liquid. And operating condition. So what is the initial temperature, what will be the changes in that condition, you can, pressure, inlet velocity, everything will be given in the operating condition. And also you need to define the boundary condition. We will explain these things when we enter into that CFD environment, that GUI. So I will explain in that condition. And initial value and previous solution, and set up the solver controls, and you are looking for that convergence monitor. Okay, so that is the steps which is involved in the setup and solve. The next thing is compute the solution. It's a major task. Okay, always usually you can't expect all the problems should be converged. So sometimes if you are really lucky, your problem will be converged. So the convergence is only happen if all the factors is correctly assigned. So otherwise the problem will never converge. So the discretized conservation of equations are solved iteratively until its convergence. Okay, so what is the term convergence and what is iterative? So we already studied about iterative. CFD is actually uses iterative solvers. So I'll explain as simple as possible. Let's say we have an example, equation like this: ax plus b is equal to 0. Usually we know the value of a and b, we can easily calculate the value of x, right? So we can easily calculate the value of x by substituting the value of a and b, and solve this equation, we will get the value of x. But in CFD, what happens is we don't usually know the value of a and b. So the three values we don't know. We need to solve this problem. Okay, so what software will try to do is, software will assume the value of a and put some value for x and b dash, and try to solve this problem. Whether it is satisfies, it can okay with this x, or else if you don't satisfies the equation, it goes changes the value of a and uses the same value of x again and another value of b. So now it satisfies, it's okay, until this is iteration 1 and this is iteration 2 and this is iteration 2. So the value of x should be equal for the equation number 1 and 2. So that means if it is okay, the x1 and the x2 is equal to each other. For example, maybe the x value should be 5 and 5. That is okay, the equation is then satisfied. We call it as a convergence. But usually it doesn't happen on a single 3 step, 4 step. It will take 200 steps, 200 iteration or 300 iteration. Sometimes 5000 iteration also happen to guess the exact value. So that is what iterative method means. It is the first iteration, second iterations. So the convergence is reached when the changes in the solution variables one iteration to the next negotiable. So the negotiable values here is 10 to the power of minus 6. So when the difference between the two values like x1 and x2, even it cannot be equal, but it can be a negotiable value changes, maybe even o. So that is a value of 5.00000012. Maybe the next value may be 5.00000024. We can call it as, okay, these two values are equal to each other. The problem is say it as a converged one and assumed as a converged one. And overall properties convergence achieved, and the quality of interest what we are looking for is a drag pressure drop we can reach safely, but it's only visible when the problem is converged. What are the factors which affects the convergences? The appropriateness, then accuracy, and assumptions we made, meshing resolution obviously, and numerical errors. So if you have some numerical errors, the problem will not converge, and you don't have a well and good mesh, it will affect your convergence. And also the assumptions you made. So the lot of assumptions you made, the problem will easily converge. If you don't have a less number of assumptions, so the problem will get more complicated to converge. Okay, so that is what they actually explained in this slide. So that is step number 6, and I will move on to the next. Step number 7, examine the results. It's again very important. So we have a post processing environment, that is CFD post. A CFD post is used to view the results. Basically the numerical method gives the numerical data, so you can't view the data directly. You need a certain tool to decode that numerical data for a user interface, like a graph and then cool animations we can create from this environment. And we can analyze the flow of the pattern, especially if it is a liquid. We can analyze the overall flow pattern, and if there is any separation between the model and the fluid, we can, and shocks, shear layers, etc. we can define. So right from the temperature related things, contours, graph related things, everything we can view from the result environment, that is CFD post. So usually the entire data from that solution will transfer to the CFD post, and you can create a different graphs and contours in that particular region. Here also you see a picture, right? So this is the airfoil structure. So the air is actually flows over here, and the flow of the air and the maximum velocity and then minimum velocity, where the pressure is maximum, where the pressure is minimum. So that will be seen in this animation using the color contours. Okay. Yep. So we'll come to the end of the session. So today what we seen is, it's an introduction to a CFD, and why we use CFD and what is CFD, and what are the steps which should I remember while do a CFD analysis. So we have a 7 steps which should be on our mind before enter into a CFD analysis. Okay, so that is all for this session. We will meet on our next session.